Hello everyone, I think everything is going well with you. Today we'll start a new chapter called the solid state physics, and believe me, this is much more entertaining and very important for every branches of engineering. In this lecture, we will restrict our discussion on crystal structure as a part of the solid state physics. If we go through the periodic table, and I am sure that you are all familiar with the periodic table, we'll find that there are 91 elements which are metals, and they possess the characteristics of high electrical and thermal conductivities. Not only the metals, if you go through the periodic table, we'll find the different elements, so different external properties like the electrical, magnetic, optical, thermal properties. And if you go through the proper scientific investigation, you will find that the external properties are the manifestation of the internal arrangement of the constituent particles. As we know that each and every materials build up of a large number of atoms, molecules and ions, and we will find that the external properties, that means the behavior of optical behavior, their thermal behavior, all are depends on the internal arrangement of the constituent particles. So in this study, we will restrict our discussion on the solid states of the material. And the solid materials broadly categorized in two classes. One is the crystalline and another one is the amorphous. As we know, in the crystalline material, the constituent particles, and these particles may be atoms or maybe molecules or ions, are regularly arranged. But in amorphous case, the regular arrangement breaks down. In this study, we will confine our discussion only on the crystalline materials. So let's again remember what is the crystal structure. Crystal structure where there is a regular arrangement of the constituent particles, that is the atoms, molecules or ions. And our aim is to make a relation between this arrangement of the constituent particles and the external properties, that means the magnetic, thermal, optical properties, how the internal structure reflects the external behavior of the material. So for that, first we have to analyze the internal arrangement of the particles, that means atoms, molecules or ions. So how to analyze this one? Is there any tool to analyze this internal arrangement by which we can explain the external properties of the materials? Yes, we are lucky enough that in mathematics there is a discussion on the regular arrangement of the points in space. In mathematics, there is a lots of discussion on the regular arrangement of points in space. So if we observe carefully, we will find that in our real crystal, there is also a regular arrangement of constituent particles. And in mathematics, there is a discussion on the regular arrangement of points. And this regular arrangement of points in mathematics is called the lattice. So, if anyhow we can relate these two things, that is the mathematics of the lattice and the regular arrangement of the points, then our problem will be solved. So let's try in this way. In mathematics, we have the discussion on the lattice points, and in reality, in place of points, we have the real entities like the atoms, molecules or ions. So now, if we place this real entity in the lattice points, then we can make the real crystal structure. So this is the lattice and the real entities are called the bases. So if we add them, we will get the real crystal structure, which is the lattice plus bases. So let's try to analyze the real crystal structure in this way. Hence, we got some tools to analyze our real structure. Now we will develop another concept which is called the unit cell. If we consider the lattice structure, we will find that the whole structure can be found out by repetition of a smaller unit. In this structure, if we consider, so this is the lattice structure where there is a regular arrangement of the points, and if we consider a small unit of square shape, we'll find that if we repeat this small unit, we will get the whole crystal structure. So in other words, we can say that is the whole crystal structure is the repetition of this small square element, and this small square element is called the unit cell. So unit cell is a building block of the crystal structure. Let's move to the three-dimensional case. For convenience, if we consider the cubic crystal, we'll find that the whole crystal is nothing but the repetition of this small cube, and this is the unit cell for this 3D structure. And our aim is to define the external properties of the material through the internal structure, and it is sufficient to study the unit cell in place of whole structure. So if we study or analyze the unit cell separately, then it will be sufficient that to analyze the whole crystal structure. So let's draw the unit cell separately, and for convenience we have taken the cubic unit cell, and we will find there are mutually orthogonal three axes which are A, B and C, and by varying this A, B, C, we can change the size of the unit cell, and there are three angles alpha, beta and gamma, and just varying this alpha, beta, gamma, we can change the shape of our unit cell. So these 6 parameters, that is A, B, C and alpha, beta, gamma, gives the different shape and size of the unit cell, and A, B, C can be take any values from 0 to infinity, alpha, beta, gamma can take any values. So there are an infinite number of possibilities based on this ABC and alpha, beta, gamma of unit cell. So if we want to analyze the 118 elements of the periodic table, so it's not is a tough job that we have to remember large number of A, B, C, alpha, beta, gamma for different materials. But don't worry, nature is kind enough. We don't need an infinite number of set of A, B, C and alpha, beta, gamma. Rather, we need only 7 different structures, that is 7 different values of A, B, C and alpha, beta, gamma, and through these 7 different structure we will be able to analyze or we will be able to express all the elements in the periodic table as well as in the universe. So is not it as a good thing? So this is called the 7 crystal system. So all the crystal structure are in the category of only 7 different crystal structure. And in this 7 crystal system, we have considered the corner atoms only in the unit cell. So for example, if this is the unit cell, there are atoms at the corner of the unit cell. So there are 8 atoms at the 8 corners of this cubic cell. And in the 7 crystal system, we have taken only the corner atoms, and we think there are no other atoms at the center, at the face of this unit cell. But the French mathematician Bravais considered the off corner lattice points also, and he got the total 14 numbers of lattice structure. So in this 7 crystal system, so crystal system is 7, and if we consider not only the corner atoms but other atoms, then we will get the 14 different crystal structures, and these 14 different crystal structures are called the 14 Bravais lattices. Is it okay? And how these another atoms can take place? So this may be in 4 different ways. One is that if there are only the corner atoms, we called it the simple cubic structure or simple crystal structure, and if along with the 8 corner atoms, if there is another single atom at the center of the body, then it is called the body centered crystal structure. And if there are atoms at each face of the cube, then it is called the face centered crystal structure. And if there are other atoms only at the two surfaces, that is the top and the bottom surfaces, then it is called the base centered crystal structure. So along with the 7 crystal systems, if we consider the off corner atoms also, then we will get the 14 Bravais lattices. So let's see how the 7 crystal systems are formed with varying parameters of A, B, C and alpha, beta, gamma. So we can tabulate all the 7 crystal systems in this table. So first take the lattice parameter is as follows, where all the A, B, C are equal and alpha, beta, gamma are 90 degree. And this crystal system is called the cubic system. And there are 3 subsystems of this cubic system. This is simple cubic, body centered cubic and face centered cubic. Example of the cubic crystal system is gold, silver, copper, etc. Most of the metals are under this cubic system. Next, move to the second crystal system, where A equal to B but it not equal to C and alpha, beta, gamma are 90 degree. And this is called the tetragonal, and their subsystems are simple cubic and body centered crystal. And the example is titanium dioxide, stannous oxide, etc. In the third system, where A not equal to B not equal to C, alpha, beta, gamma are 90 degree, and this is orthorhombic, and the subsystem is SC, BCC, FCC and base centered. And the example is potassium nitrate, potassium sulfate, etc. In the fourth system, A equal to B equal to C, alpha, beta, gamma are equal but not equal to 90 degree, and this is called the trigonal. And there is one subsystem which is subsection which is simple crystal structure, and the example is arsenic, antimony, bismuth. In the fifth one, where A equal to B not equal to C, alpha, beta are 90 degree and one of the angle, that is let's say gamma, is 120 degree. It is the hexagonal, and the example is SiO2, that is silicon dioxide, zinc, cadmium, etc. and the subsection is simple cubic. In the sixth crystal system, we will find A not equal to B not equal to C, alpha equal to gamma equal to 90 degree but not equal to beta, and it is named as monoclinic, and there are 2 sections, simple cubic and base centered. And the example is calcium sulfate with 2H2O. And the seventh one is the most general one, and where A not equal to B not equal to C and all angles are not equal and also not equal to 90 degree, and it is the triclinic, and it is one section only, simple crystal structure. And the example is blue vitriol or CuSO4 5H2O. So we have discussed here all the 7 crystal system with considering off corner atoms also, and we will find, if we count, there are 3 subsection, that is SC, BCC and FCC, 3 to 5, and there is 4, that means total 9, and again there is 1, that is 10, 11 and 13 and 14. So in this 7 crystal system we will get 14 Bravais lattices. So if there is any question how many crystal systems are there, so the answer will be 7 crystal systems are there. And how many Bravais lattices? 14 Bravais lattices are there. So we have seen the 7 crystal systems, and we have also learned that it is enough to analyze the unit cell of any crystal structure. And to analyze the unit cell, there are some important parameters, and we have to go through these parameters. So first parameter is that we have to know the number of lattice points per unit cell and the volume of the unit cell, number density of the lattice points, and the fourth one is the packing fraction, and fifth one is the coordination number. So first consider the number of lattice points per unit cell, and for simplicity we consider here the cubic structure only. At a glance, if I ask you that what is the number of lattice point per unit cell, and there is a chance of mistake that if we consider a unit cell of the cubic structure And if we take the simple cubic structure, then we will find there are 8 atoms at the 8 corners, and we think that there are 8 atoms per unit cell, but this is the wrong. If we analyze in details, that is, if we want to get the number of lattice points of this unit cell which is highlighted here, it is not the 8. If we observe very carefully, we will find, let's check, we want to find out that number of lattice points of this unit cell. Okay, so we will focus on that atom which is represented by A. This A atom is a part of this highlighted unit cell, and this A atom is also a part of the second unit cell which is here, and this same A atom is the part of another unit cell which is designated by the 4. Okay, and A is also a part of this unit cell, right? So here we find out that A atom is a part of the 4 unit cell. Let's say, is there any other unit cell for which A is also the atom? So we will find out that this same A atom is a part of this 5th unit cell, right? If we consider this unit cell, A is also one corner atom. Similarly, this A atom is a part of the 6th unit cell. If we consider this unit cell, it's not it. I think we will get, okay. So again, if we consider this unit cell, this is the 7th unit cell, this one, and this is also a part of this 7th unit cell, and at last this A atom is a part of this 8th unit cell, right? Okay, so we find that the same A atom is sharing by 8 nearby unit cells. So the sharing part of this A atom per unit cell is 8, 1 by 8. So A atom, that is any single atom, is shared by 8 unit cell. So the sharing of this single atom by single unit cell is 1 by 8. And in a single unit cell there are 8 atoms, and each of them shared by the 8 more unit cells. Hence the number of atoms per unit cell is 8 into 1 by 8, which is 1. Similarly, if we go for the body centered cubic cell, we will find there are an extra atom which is at the center of the unit cell, and there are 8 atoms at the 8 corners, and each atom is shared by 8 unit cell, and there is 1 atom at the body center. So the number of lattice points per unit cell becomes 8 into 1 by 8 for the corner atoms, and the single atom 1. So this is the 2. So number of lattice points per unit cell for the BCC structure n is equal to 2. Similarly, if we consider the face centered cubic structure, there we will find there are 8 atoms at the 8 corners, and each of this atom is shared by 8 unit cell. So the number of atoms per unit cell due to corner atom is 8 into 1 by 8, which is 1, and there are 6 atoms at the 6 faces, and each of them shared by the 2 faces. That means if we consider this face, this is the part, this face is shared by the 2 consecutive unit cell, So this atom is shared by the 2 unit cell, hence the sharing per unit cell is half. Hence 6 atoms at the 6 faces, and each atom of them shared by the 2 faces. So the number of atoms per unit cell becomes 6 into half. This is 3. Hence the total number of atoms per unit cell for the FCC structure, this 1 is due to the corner atoms and this 3 is due to the face centered atom. So therefore the total number of atoms per unit cell becomes 4. So next move to the next parameter, which is the volume of the unit cell. Since we have taken the cubic structure, hence A equal to B equal to C, all lattice constants are same, and if we consider this is A, so the age of this cube becomes A, and the volume of this unit cell is nothing but A cube. And the third parameter, which is the number density of the lattice points, and which is defined as the number of lattice points per unit volume. So for structure, we have calculated the number of lattice points per unit cell is 1, and the volume of the unit cell is A cube. So the number density of the lattice points rho n equal to n by v, that is 1 by A cube. And for the body centered cubic structure, as we have seen, the number of lattice points per unit cell is 2, and here also v is equal to A cube because it is also a cubic structure, and rho n becomes 2 by A cube. Similarly, for the face centered cubic structure, we have get that n equal to 4, that is the number of lattice points per unit cell is 4, and the volume of the unit cell is A cube. So the number density per unit cell is 4 by A cube. So we have discussed 3 important parameters to analyze the unit cell, that means to analyze the crystal structure, which are number of lattice points per unit cell, volume of the unit cell, and number density of the lattice points. In the next class, we will discuss 2 more important and very important and also very entertaining parameters, which are the coordination number and packing fraction. And thank you for your attention, and we will meet again in the next class.